So again, good Monday morning, start of a new week. Hopefully, everybody had a good weekend. And what we're going to do today is hopefully going to calculate beam stress in beams. That's the the main topic today. Also, just I was looking schedule wise, as far as you're curious or want to know when our next test is coming up. My best guess would be Monday or Tuesday of next week. I can't tell you 100% for sure right now, um, but I suspect we'll know 100% for sure by Wednesday. So just kind of keep that in the back of your mind, unless something unexpected happens or comes up. Monday or Tuesday next week is looking like, again, one of those 2 days will be where our next test is. So we'll know for sure later this week. We'll see as we got to get through chapter 6 and 7, talk about bending stress and then shear stress. All right, so sort of quick reminder, review a little bit since, again, it has been a few days since we last talked about any of this. But in your textbook, the sections we're in is in chapter 6, sections 3 and 4. And what we spent most of Friday doing was developing this formula for bending stress. So if we're looking at some beam, and again, the cross section, I'm doing rectangular because it's easy to draw. It doesn't matter. But our coordinate system, we oriented. So the x is the longitudinal, the axial direction. When you're looking at the cross section, y is the vertical direction, positive up. And the z would be our horizontal direction. And this axis, the z-axis, that's what we call the neutral axis. That's the axis that separates tension and compression when you're bending this beam. And one of the things we saw and verified or proved was that that neutral axis goes through the centroid of that cross section. We also define this direction as being a positive moment, one that bends it so that it's concave up is considered a positive moment. And we came up with this formula that the normal stress due to that bending moment was minus my over I. And this formula, using this sign convention and this orientation of the axes, will give you a positive stress for tension and a negative stress for compression. And y is the bending moment, m is the bending moment, y is positive up away from the neutral axis, and I is the moment of inertia for that cross-sectional area about that neutral axis. So in order to calculate this normal stress due to bending, one, we've got to be able to locate the centroid of the cross-section, because that's how we know where to place our neutral axis. And we have to be able to calculate moments of inertia. Those were two things that you were supposed to learn in static. And I wanted to, I suppose, maybe take about 5 minutes or so and give you a real quick review, refresh your memory on how to accomplish those two things. Because, again, those are two things that you have got to be able to do. So let's take a few minutes, and talk about, one, how to locate or calculate where the centroid of a area is. Now, if it's a nice rectangular cross section like this, then we don't really have to do any calculations. We know it's right in the center. It's halfway. So anytime you can use symmetry like that, do so. There's no need to calculate it. But if you have a cross section that's not symmetric, and you do have to calculate it. All right, this is how we're going to do it. And this is, again, formula you should have seen in statics. We're not going to have to integrate anything. All of our cross sections are going to be areas that we can break up into a finite number of rectangles or circles or triangles, something like that. You don't see many beams with cross sections that are defined by a function that you would have to integrate, and we're not going to see any in this class. So, just for example, if say we had like a T-beam, we had a beam, whose cross section, kind of shaped like a T. Well, if you want to locate where the centroid is, and just looking at it, I see you have more area near the top than the bottom, so I know that the centroid is going to be closer to the top than the bottom. It's not going to be right in the middle, halfway. Right? So again, that's where we would put our neutral axis. But we need to know how to calculate y bar. That's our centroid location. Well, you just break it up into pieces. In this case, we could break it up into two rectangles. We'll call this A1, this A2. And then we just have to locate the centroid of each piece. So the centroid of rectangle 1 would be right in the middle of rectangle 1. That's what the y tilde here is in this formula. It's the location for the centroid of each piece. Likewise, for area 2 up here, we need to know what that distance is. That's the distance to the centroid of area 2. And then it's just a matter of, again, summing those things up. You take A1 times y tilde 1 plus area 2 times y tilde 2, divide by the sum of the area. Right? If you had 3 pieces, you do 3 or 4 or whatever. But that's how you locate where the centroid of an area is. Any question about that? All right. So again, this is something, if you can't do this, you can't solve these problems. So the other thing was we had to be able to calculate moments of inertia. Take a couple of minutes to talk about that. Now again, the integral definition is integral y squared dA. And we came up with that integral when we were driving this formula. We replaced it with I. But as I said, with the centroids, we're not going to have to integrate anything. These areas are going to be some combination of these simple common shapes. And many of these shapes, common shapes have been integrated for us. And the results are in a table. Now, there's extensive resources out there where you can get formulas for moments of inertia for lots of different shapes. But there is a small table in your textbook. This is, if you have a hard copy, inside the front cover of your textbook, you'll see a table. I actually got a copy here, and I'll show you what it looks like. All right, this is from, again, inside the front of your book. And over here on the right side, you'll see these common shapes. You got rectangles, triangles, a trapezoid, semicircle, circle. They even give you a couple of parabolic shapes down here. Again, probably not going to see anything like that on a cross section of a beam, but hey, it's in there. So that table is in the front of your book, and over here to the right, you'll see formulas for moments of inertia about these axes. And so that resource is available to you when you're working these homework problems. If you got something you don't know the moment of inertia for a semicircular area, then you can go to this table and you can find it if you need to. All right. Now, one of those that I expect you to know is a rectangle. All right. So this one I expect you to know without that table. So if you've got a rectangle, and we'll call this the z-axis goes through the centroid, and this rectangle got some width b and some height h. I expect you to know that the moment of inertia about that z-axis, the horizontal axis through the centroid, is 1/12 base times height cubed. And trust me, if you work anywhere close to the number of problems that you're supposed to be working, you won't have any problem remembering that one because you're going to see it a lot. Think about it. I'd say probably 90-something% of all beams, if you look at their cross section, it's some combination of rectangles. And so you're going to use this one repeatedly over and over and over again. And again, by test time, trust me, if you're working problems, you'll know this one. Now, anything else I would provide to you. Okay, so keep that in mind. Any other shape, that table would be provided. All right, so anything other than a rectangle, don't worry about knowing the formula for the moment of inertia. That table would be provided to you. But if it's a rectangle, I expect you to know. All right? Any questions about that? One other additional thing that we need related to inertia, again, if you go back up here to this example, or my T-shaped cross section, we need the moment of inertia about the axis that goes through the centroid of that whole cross section. Well, that axis doesn't go through the centroid of either one of those rectangles, area 1 or area 2. So to get around that, we need what's called the parallel axis theorem. And again, this is all stuff that, and from this point forward, anytime I refer to the parallel axis theorem, I'm just going to abbreviate it PAT. You should know this, but again, I think it's maybe beneficial to take a minute here. What that does is if you've got some area up here, and again, it doesn't matter what it looks like, most of what we'll be dealing with are rectangles, but this applies for any shape. And so if this is the centroid, and this is, say, the z-axis that goes through the centroid, but we want to find the moment of inertia about some axis down here. It does not go through the centroid of that area. That's what the parallel axis theorem does. It allows us to do that. We can get the moment of inertia about the z-axis down here, some distance away from the axis that goes through the centroid, by taking the moment of inertia about the axis that goes through the centroid, which we would get from, if it's a rectangle, 1/12 base times height cubed, or if it's not a rectangle, that table. But we got to add something to that. And what we add is the area times this distance squared. So whatever that perpendicular distance, in our case, it's going to be the vertical distance, between those two axes, we got to take the area times that distance squared, and you add that to get the moment of inertia about this axis. All right, so that's all, again, quick review of how to locate centroids and how to calculate moments of inertia. So before we work a problem, Again, any questions about how to do either one of those two things? All right. So if you need a second, speak up. Otherwise, I'm going to go to a new sheet and we'll start working a problem. Okay. All right. So let's see if we can do this one. Yeah, this is a kind of a strange looking cross section. But what we're asked to do here is to find the maximum tensile and compressive bending stresses. All right, so we're going to be given this cross section, and we want to find what's the maximum tensile stress, what's the maximum compressive stress. All right, so let me attempt to draw this cross section. Again, it's kind of an unusual shape, kind of looks like pi. And I am sure confidently before I finish, my picture won't be to scale. This, well. All right, so again, that's what our cross section looks like. And again, kind of looks like pi. So I need to put some dimensions on here. And I'm going to go ahead and draw my axes. Because again, looking at it, I know the centroid is going to be closer to the top than the bottom. But where it is, I can't look at it and tell. We're going to have to calculate where that centroid location is. So this is my z-axis, or the neutral axis. Goes through the centroid. My y-axis is vertical. And it's symmetric horizontally. Obviously, it's not symmetric looking at it up and down. But we need dimensions. 10 millimeters. 10 millimeters. 20 millimeters. And same thing on the right side. This would be 20. This is 10. And this is 10. This top flange up here is 10 millimeters. And here to the bottom is 40 millimeters. And let's see, I think maybe it's all the dimensions we have. We'll find out in a minute if I left one off. All right, so again, this is what our cross section looks like. Our beam, again, if you were looking at this, this is what it would look like. This is some beam. We're just looking or being shown what the cross section looks like. And we got a moment that's going to be applied this direction. We're going to bend it this way, and the magnitude of that moment is 75 Newton meters. All right. All right, so while everybody finishes, if you haven't, drawing what this cross section looks like and putting your dimensions on there. Just a question you should be able to answer at this point before we do any calculations. Right? If we're trying to find the maximum tensile and compressive stresses, right? And so somebody's going to have to unmute and chime in here. Where would the maximum tensile stress be on this cross section? All right, now everybody don't answer one. All right, somebody doesn't volunteer, I'm on.
At the top?
The maximum tensile stress would not be at the top.
Close to the neutral axis?
No, the stress at the neutral axis is zero. Right? That's what defines the neutral axis. It's what separates tension and compression. At the neutral axis, the stress is zero. But if we're bending it this way, right? We're bending it like this. We're going to be pushing in on the top. Everything above the neutral axis would be in compression. So the maximum compressive stress would be at the top. So now I give you, everybody should get this for sure now. Where's the maximum tensile stress going to be?
Bottom.
At the bottom, right? You're going to get your maximum tensile stress along this bottom surface of the cross section. Your maximum compressive stress is going to be right there along the top surface. Again, at the neutral axis is zero. Right? So we've got to calculate where this centroid is located, because that's where our neutral axis is. And if I don't know that location, right, I don't know how far it is from there to the top, how far it is from there to the bottom. Right? That's what's got to go in the formula, minus my over I. Right? We want to get the stress, I got to know what y is. So first thing we need to do, right, is we got to calculate what y bar is. Where is this centroid located? Right? So here we can break this thing up into, looks like, again, there's multiple ways we could do this. We could think of one big rectangle and subtract out 3 rectangles, but that's 4 pieces. It's probably more efficient if we do it like this and just break it up into 3 rectangles. Then we only have 3 pieces. Right? So, for identification purposes, I'm going to call this rectangle 1, this rectangle 2, and the top up here, rectangle 3. Right? So when we're calculating y bar, we need to know what the area of each piece is and where the centroid of each piece is located. That's what the y tilde is. So I know the centroid for area 1, it's a rectangle. It's going to be located right in the middle. Well, if this rectangle is 40 millimeters tall, that's going to be 20. So the area, again, it's a rectangle. It's 10 by 40? So it would be 10 by 40. That would be the area, A1. And then y tilde 1 would be 20. Right? This is just A1 times y tilde 1. Right? And we just do that for all 3 rectangles. Well, area 2 is identical to area 1. Right? So don't need to think about this. It's just, in fact, we could just multiply this by 2 if you wanted to. Right? But area 2 is 10 by 40, and its centroid is 20 millimeters, half of 40 from the bottom. And then we got area 3 up there, which this is 10, 20, 40, it's 80 wide, 10 tall. So the area is 80 times 10. And its centroid, right, is located right in the middle of area 3. So that distance would be 40, and then plus half of 10 is 5. That'd be 45. And then we just divide by the sum of the area. So this is what, 400, 10 times 40 is 400, and 10 times 80 is 800. And then you pull out your calculator, crunch the numbers, and I got, it was 32.5 millimeters. So that is calculated from the bottom. If you want to do it from the top, you can do it from the top. It doesn't matter. We just need to know where it's located from one or the other. Because if we know one, we can get the other. But we need to know where it's located. So this is, again, this would be from the bottom. That's where the centroid is located. That's where my neutral axis is. Any question how we calculated the neutral axis location? Okay, well now let's go ahead and let's get our moment of inertia, because that's what this I is in this formula. It is the moment of inertia about that neutral axis. And that's why we got to know where it's located before we can calculate what I is. So we want the moment of inertia, again, about that neutral axis. Now, here's where we have all rectangles. All right, so I know moment of inertia about the axis that goes through the centroid of a rectangle is 1/12 base times height cubed. But notice the centroid of these three rectangles none of those three lie on the axis we're calculating. So we're going to have to use a parallel axis theorem. So for rectangle 1, I got 1/12 base times height cubed. Well, the base is 10. And up to you, you can leave all your dimensions in millimeters. If you do, you're going to get a really, really large number. And to plug in this formula, we're going to need to convert it into meters to the fourth instead of millimeters to the fourth. So eventually, it's going to have to be in meters. So up to you, leave it in millimeters and convert to meters at the end, or we can go ahead and put everything in meters now. I think that's what I'm going to do, is I'm going to go ahead and put everything in meters. So the base, 10 millimeters, is 0.01 meters. So 1/12 base. The height of rectangle 1 is 40.04 cubed. All right, so that's my 1/12 base times height cubed. All right, but this centroid, it does not lie on the axis I'm calculating. So I need to know what that distance is. I'll call it D1. Right, that's the distance that the centroid of area 1 is away from the neutral axis. So I got to add the AD squared here. So the area is 0.01 times 0.04. Right, that's A1. And now I need to know what D1, and then I got to square it. So D1, right, that distance, well, we just found here, right, this Y bar turned out to be 32.5 millimeters. So that's the distance from the bottom to the neutral axis. Well, the distance from the bottom to that centroid is 20. So that distance is just a difference. So it'd be, if we go in meters, 0.0325 minus 0.02. And we got square it. Don't forget square it. That's D1 squared. All right, so this would be for rectangle 1. All right, so what I've got here, again, that's for rectangle 1. 1/12 base times height cubed plus AD squared. Any questions where any of those numbers came from? Well, when we go to area 2, just like we did up here with the centroid, it's identical to area 1. And so up here, I just wrote it again, but here I'm not going to rewrite all that stuff. We're just going to do 2 times that. And say that.
Could you explain the D in that equation, please, again?
It's the distance from the neutral axis, the axis we're calculating the moment of inertia about, the distance from that axis to the centroid of that area. So it would be the distance from this axis, the neutral axis, to the centroid of area 1, the distance to the centroid of area 2, and the distance to the centroid of area 3. It's the distance from that neutral axis to the centroid. Yes, parallel axis there. So area 2 is identical, we'll just multiply by 2. And then to get, we need area 3 up there. Again, it's going to be 1/12 base times height cubed. Here, the base is 80 millimeters, or 0.08. The height is 10 millimeters, 0.01 cubed. And just like we did, again, for area 1, we'd have to do the same thing for area 2. The distance is the same as it was for 1, but it's not going to be the same when we're looking at area 3. That's what that distance is. It's from that axis, our neutral axis, to the centroid of that area. So we got to add the area, which is, again, 80 times 10 millimeters. Now that distance would be the difference between, that was 45 millimeters from the bottom to the centroid of area 3. So to get that distance, it would be 45 minus what our y bar is, because that's the distance to our neutral axis. So it would be, in meters, be 0.045 minus the 0.0325, and we got to square it. So that's how we would get D3. We would take 45 minus 32.5, in millimeters. And we square it, right? And this is rectangle 3. And then we just add all those up. And again, if you do meters, we're going to get a really small number. I got 0.4 times 10 to the negative 6 meters to the 4th. That would be my moment of inertia for that area about the neutral axis. All right, so now we're ready to plug in our formula. And you'll see a lot of the work, majority of the actual work you got to do is statics. Right? You learn how to do this in statics. Mechanics and materials part is just plugging in this formula for stress. So per our earlier discussion, right, we said our maximum compression is going to be at the top. Right? And Y at the top is going to be positive. Right? Remember, Y is positive up. So this would be Y to the top is just the distance from our neutral axis to that top surface. Well, it's 50 millimeters tall, and Y bar was at the centroid, our neutral axis is at 32, so it'd be 50 minus 32.5, which is, what's that, 17.5 millimeters, or one to be 0.0175 meters. Again, we want everything in meters when we plug in this formula. It's positive. So our maximum compression, we got minus our moment. And if you look at this moment, the direction of that moment is positive 75 Newton meters. Right? We define a positive moment acting this way. A negative moment would be in the opposite direction. So it's a positive moment. So 75 times 0.0175 and divide by I, 0.4 times 10 to the negative 6. And motivation for writing it is some number times 10 to the negative 6. If you remember, when we do stresses in metric units, we get really big numbers. And so typically we write stress in megapascals. Mega's 10 to the 6. So basically, to 75 times 0.0175 divided by 0.4 is going to give me the stress in megapascals. I got, and we do get negative. I got 3.28 is a megapascal. That's my maximum compressive stress. It's going to be at the top surface. And as we discussed previously, the maximum tension is going to be at the bottom. So Y bottom is going to be negative. Right? This I did blue. Right? So, you know, my origin's here. So Y bottom is going to be a negative, whatever Y bar is. It's going to be negative 32.5 millimeters or 0.0325 meters. It's negative. And we plug in the formula. So our maximum tensile stress is going to be minus 75 times a negative 0.0325 divided by I. And you see, we get a positive. And I got a little over 6 point, we'll just say 6.09 megapascal. So that's going to be my maximum tensile stress. It's going to occur at the bottom of that cross section. Right. So again, looking at this, this is the mechanics materials part. This is what you were supposed to already know how to do from statics. But you got to be able to do both, or you're not going to be able to solve it. Question about that one?
Could you
Go ahead.
could you explain the Y top again?
It's the distance from the neutral axis to the top surface.
Okay.
There's no other way to explain it. And Y is positive up.
All right.
So it'll be whatever the positive distance is from the neutral axis to the top surface. Right? If you don't go all the way to the top, you know, say if you went, you wanted to know what the stress was here at this point, then instead of using Y top 17.5 millimeters, you'd take whatever that distance was and plug that in here for Y, and that would give you the stress at that point. Obviously, it would be less than 3.28. Because again, it's a linear relationship. The further you get away from the axis, the larger the stress is. So the stress at C is 0, because Y is 0. So the stress at this point is 0. Anywhere along this axis, the stress there is 0, because Y is 0. Right. Any other questions about that one?
Is compression always going to be at the top?
If the moment is in this direction, yes. Right? If your moment is acting this direction, you're compressing the top and you're stretching the bottom. If the moment's in the opposite direction, the opposite would be true. See if I can squeeze it in here. Say we had this cross section, but our moment was acting that direction. If our moment's in that direction, it's a negative moment, and it's causing tension at the top and compression at the bottom. Right? Because if you're bending it in this direction, you're pulling on the top and you're pushing in on the bottom. Make sense?
Yes, sir.
All right. Any other questions? All right. Well, I think we got time to do one more. This one's not the calculating the centroid and moments of inertia for this one are a lot shorter and simpler. But I think we got time to go through and do this one. So here we're just asked to find the maximum bending stress in the beam. All right, but this time we're actually given not just the cross section and what moment's acting on it, we're actually given the beam and the loading. So we got a pin support at this end, a roller here at this end, and a force of looks like 2,000 pounds acting here at B. This is 3 feet. This is 9 feet. So we got a simply supported beam, right? That is 12 feet long, and 3 feet from the left end, we got 2,000 pound force, and we're also given what the cross section looks like. The cross section is 2 by 4 inches. All right, so that's what it would look like if you looked at the end of that beam. And that's what the cross section looks like. Now, a couple of things before we go any further. One, notice the previous problem asked you to find the maximum tension and compression stresses in the beam. This just asks for the maximum bending stress. All right, so here's where you would, if you want to use the formula that's in the book that I mentioned, first I mentioned this right at the end class on Friday. There's this formula in your book. It says sigma max equals MC over I. Because what it's asking for is just what is the largest magnitude of bending stress. It's not asking for what's the largest compressive stress or what's the largest tensile stress. It just wants to know what's the maximum magnitude of stress. And here, if you're going to do this, that M is just wanting to know what's the magnitude of the largest moment. That's what M is equal. C here is just the absolute value, the largest magnitude of Y. No plus or minus. It just wants to know what's the farthest distance away from the neutral axis you can get. That's what the C represents. I is the same. It's the moment of inertia about the neutral axis. So if we're going to answer this, we need to know what the maximum bending moment is in the beam. So that's the first thing we got to do is find what the maximum bending moment is. In that example we just worked, we were told what the moment was acting on. Here, we got to find it. And how we do that is we need to draw our shear and moment diagram. That's how we find out what the maximum moment is. Well, I've got, and that's part of the reason I wanted to work this one is, this is kind of what you're going to see, in the real world is you're going to have a beam with loads on it, and you're going to have to determine what the maximum bending moment is. You're not going to be just given that maximum moment like the previous example. So we really just need the moment diagram, but if you remember, we get the moment diagram from the shear diagram. So that's why we got to draw both of them. So we need to know what AY and CY are. So not real complicated. Sum of the moments about A. And I got CY times 12. And then minus 2,000 times 3 equals 0. And it's all for CY. 6,000 divided by 12 would be 500 pounds. So I know CY here is 500. and then sum the forces in the y. I'm going to go positive up. AY goes up, CY goes up, and then 2,000 down. Looks like AY is going to be 1,500. So I know AY is 1,500 pounds. And now we can draw our shear diagram, and then from that we get our moment diagram. So, yeah, this is the shear force. These are in pounds. And we got A, B, and this in C. So I know the shear force is going to be equal to that support reaction. So we're going to start at 1,500. Go straight across, doesn't change till our load changes. And we go straight down 2,000. Puts me at minus 500. And notice that does check with CY. And now we know this is 3 feet. This is 9 feet. And we need those dimensions because, remember, to get the moment, these would be in foot-pounds. So don't forget, put units on your shear moment diagram. Let's see. The moment increases or decreases by whatever the area is under the shear diagram. So this area, what we call A1, it's a rectangle. 1,500 times 3 is 4,500. So we're going to go up 4,500. Now it's going to start at 0. Because if you look at our beam, there is no moment at the end of that beam. It's a pin support. There's no applied moment there, moment 0. And remember from last week, we know that the shape of the curve is 1 degree higher than the shear diagram. If the shear is constant, moment's linear. So it's a straight line. Goes from 0 up to 4,500, because that's the area. Now here, that area is going to be negative, and we're going to go down that amount. And the area, 9 times 500 is 4,500. So we're going down 4,500. This is constant, and this is linear. We're going to draw a straight line. And if we go down 4,500, it takes me back to 0, which is that's what we should get, because there's no moment at the end of the beam. So from my moment diagram, I know the maximum bending moment here is 4,500 pounds feet. So looking at the cross section, here's where, again, the work is a lot quicker because just from symmetry, right? I know the neutral axis goes through the centroid, but it's a rectangle. Centroid's right in the middle. If this is 4 inches tall, I know this is 2 inches, and I know this is 2 inches. Right? Just from symmetry. We don't have to calculate where the centroid is. Right? So I know from looking at my picture now, I know C, which is Y max, is 2 inches. It's a rectangle. So I know, if you don't know yet, you will know soon, again, that here the moment the neutral axis goes through the centroid. So here, this is just 1/12 base times height cubed. Right? We don't have to add AD squared because it is through the centroid. So it's just 1/12. The base is 2. The height is 4. And that's 10.666, so 10.67, whatever you want to round it off to. Okay. So now I want to use this formula, sigma max equals MC over I. I know the maximum bending moment is 4,500, but those are foot-pounds, so be careful here. Everything else is in lengths in inches, so you might want to multiply that by 12, and that comes out to be 54,000 inch-pounds. Because all our other lengths are in inches, so we need everything to be compatible. So 4,500 times 12 or 54,000. C is 2 inches, because again, it's the same to the top or the bottom. Now, if those were not the same, we'd use whichever one was bigger. But it's the same, and they're both 2. And then divide by I. And I got 10,124.7 needs to be PSI. That is the maximum bending stress in this beam. It's going to occur on the cross section there at B. If you're looking longitudinally down the beam, that's where our maximum bending stress is going to be. So on that cross section at B, and that's what its magnitude is. Now this one, since our cross section is symmetric, it's going to be the same at the top and the bottom. So if we're bending it this way, you see we have a positive moment. Our maximum compressive stress would be at the top, and it would be negative 10,124.7 psi. And maximum tensile stress would be at the bottom surface, and it'd be a positive 10,124.7 psi. But this problem didn't ask that. It just wanted to know what the maximum stress was. And we found it. Any questions on this one? All right. Any questions in general having to do with calculating bending stress? Tomorrow we're going to start talking about shear stress. All right. Well, then that's where we're stopping today. I'll end the recording. As always, if you got questions about something else, you want to stick around in just a minute or two, I'll be able to address those. Otherwise, have a good day. We'll see you tomorrow. Or I won't see you, but we'll hear each other tomorrow.